the morning session of the second day of our gravitational wave workshop. So I can say that our belief is that we will be back in person for those who are able to attend in person tomorrow. But it will obviously be a hybrid event because we know that a number of participants did not travel to Auckland. So tomorrow will be online as today, but also people who are physically in Auckland can attend on campus, and that there will be catering and opportunities to interact in person, which is obviously a key part of this effort. I've been super interested to hear the presentations over the first couple of days. We're now pleased to be continuing the morning session focusing on observables. I should start also by just introducing myself. I'm Richard Easter. I'm professor at the University of Auckland. I'm one of the people who helped put together the program that we have doing LISA-related science, which is supported by the Marston Fund and led by Renata. Obviously, it's great to see people participating in this from around the country. And one of our goals in doing this is obviously not just to do science, but also to be able to look at new connections that we've created inside of our community in New Zealand and internationally. And so this event is really an opportunity to underline the kind of broader networking that is happening as a result of the science. And in particular, I know it's already been said, but just thanking Frauendiener again, who's organized this workshop, but also contributed funding from resources that he'd secured in order to make this work. So we're very much hoping it will be a regular thing in one form or another, and very much looking forward to what the future holds. And speaking of what the future holds, right now it's my absolute pleasure to introduce Dr. Emily Kendall, who is a postdoc at the University of Auckland, was also a PhD student at the University of Auckland, and stayed on due to the insecurities created by COVID. So COVID's disruption is our good fortune as part of the LISA program at Auckland, and then Emily is spending a little bit more time with us than we might have originally expected of a PhD student. Emily's going to be telling us about the LISA program. So Emily, over to you.
Thanks, Richard. I'll just reshare my screen. Right. So can you see that? Cool. Okay. So we've already heard a number of really interesting presentations about all sorts of things gravitational waves related. And in particular, we heard a lot about ground-based detectors yesterday. And today I want to go take this as a gravitational waves past, present, and future presentation. And the future aspect of that will be the LISA mission, which I'll get to talking about soon. This title slide is just a artist's rendition of the LISA mission. And you can see it's got this triangular configuration with these what look to be extremely powerful lasers there. But this is a little bit of artistic license, and we'll get to the real parameters shortly. Okay, so to start with, I'm just going to give a brief history of gravitational waves. Some of this we've already heard, but it can't hurt to go over it again just for the sake of some historical context. So it all starts in 1687 with Newtonian gravity. So in Newtonian gravity, gravity is a force, and the strength of that force is characterized by this equation gmm over r squared. And the force of gravity in Newtonian physics acts instantaneously through vast voids of empty space. So this is so-called instantaneous action at a distance. Now, although the theory works really well, especially on the scales of sort of our solar system and things on the Earth, even Newton himself knew that there was something wrong with this. He was very dissatisfied with this formulation. And here's a quote from him at the time saying that one body may act on another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty for thinking can ever fall into it. So Newton had come up with this equation and it seemed to work really well, but there was something fundamentally wrong with it in his perspective. So fortunately, over the following couple of hundreds of years, various mathematicians and physicists started thinking more about the concept of a field. So a field is a physical quantity, which might be a scalar, vector, or tensor, which has a value for each point in space and time. So some sort of classic examples of fields, this on the right-hand side, this bar magnet with the iron filings that have been sprinkled over, and you can see these field lines exhibiting the characteristic shape of the magnetic dipole. And then below that is just a sort of wind map. And this is a vector field. So you can see both the directions of the wind by those little arrows there, and the magnitude of the wind speed by the color map. So there are fields sort of ubiquitous, and people were starting to realize that in the sort of 18th and 19th century, but we're not quite sure how far this could go and whether that could be used to describe fundamental forces as well. But people started treating hydrodynamical quantities such as fluid velocity, fluid density, and pressure as fields, and this would sort of serve as the foundation of what would come next. In these early days, of course, space was still considered to be a sort of uniform background grid, which could be indexed by a completely independent time coordinate. And as we know, that is not quite the perspective that we take in general relativity, but this is the notion that they had at the time. So this was still a promising step, because in a field theory, excitations can propagate through a field as waves rather than sort of mysteriously acting at a distance through a void. So that led to Maxwell's electromagnetism. So in 1865, James Clerk Maxwell realized that electricity and magnetism were two sides of the same coin and could be unified into a single field theory. And in that field theory, disturbances propagate at the speed of light, c. And these are Maxwell's famous equations, so relating the electric and magnetic fields E and B, which are vector fields, of course, to the charge density and the charge current. And what Maxwell realized when he was coming up with this theory of electromagnetism is that something similar may be applicable to gravity. So he said at the time, after tracing to the action of the surrounding medium, both the magnetic and the electric attractions and repulsions, we are naturally led to inquire whether the attraction of gravitation, which follows the same law of the distance, is not also traceable to the action of a surrounding medium. So basically, Maxwell was looking at the fact that the electric field falls away as 1 over r squared, and the gravitational field also falls away as 1 over r squared radially. So he sort of immediately drew parallels between these two things, but he wasn't quite sure where to go from there. Then comes special relativity in 1905. So Einstein at that point postulated that the laws of physics were the same in any inertial frame of reference. And in particular, all observers measure the speed of light to have the same value regardless of their motion. So the consequence of this is that c, the speed of light, represents an absolute speed limit. So nothing can propagate faster than light, which means that gravity surely cannot propagate faster than light. And so Newtonian gravity can't be quite right and needs to be modified. As it happens, at this time, it was actually Poincaré rather than Einstein who postulated the existence of gravitational waves, pretty much contemporaneously with Einstein's special relativity, but he didn't specify anything about their form. It was more of a musing about their possible existence. So following Einstein's special relativity, in the next decade, there were a number of mathematicians and physicists who attempted to construct self-consistent theories of gravitation. Many of these theories were scalar theories rather than the tensor theory that we are used to these days. And in these scalar theories, they included predictions for gravitational waves, but these gravitational waves were longitudinal in nature rather than the transverse ones we know to be the correct model these days. So there's a whole bunch of people involved in this. And I won't go through all of their individual contributions, but it was a very much a team effort to sort of figure out the intricacies of what was going on in this theory of gravity. And Einstein thanks a number of these people for their insights in terms of his actual generation of the full theory of general relativity. So finally, in 1916, Einstein completes his general theory of relativity, which is, again, a tensor theory rather than a scalar theory, which is where those previous attempts had gone wrong. But in his 1916 paper, there was actually no mention of gravitational waves at all. And in fact, in a letter to Schwarzschild at the time, he actually stated there are no gravitational waves analogous to light waves. Then he sort of shifted his perspective and a few months later published a paper which erroneously predicted monopole radiation within GR. He quickly realized that that was incorrect, and finally in 1918, he corrected his error and arrived at the correct formula for gravitational radiation. So on the right-hand side, we have the Einstein field equations relating the stress energy tensor to the curvature of space-time. And then below that, we have the linearized wave equation for a small perturbation h mu nu to the Minkowski metric. And this is what Jörg talked about yesterday when deriving the sort of true form of gravitational waves. Now, Einstein was still not really convinced about the existence of gravitational waves, and there was a lot of uncertainty that remained after 1918. And there was debate as to whether gravitational waves were real or perhaps a coordinate phenomenon, because as we know in general relativity, coordinates can be tricky things, and choosing the best coordinates for a particular problem is a non-trivial task. So then Einstein also sort of concluded that even if they are real, they could never be observed because they would be far too weak. The debate as to whether or not gravitational waves were real or a coordinate formulation was sort of completely settled by the 1950s. And then people started in the 60s and onwards, started to think about whether or not these could be detected. Various different types of gravitational wave detectors were proposed, but the technology was not yet advanced enough for successful detections. However, during this period, there was the observation of the Hulse-Taylor binary, which involves a pulsar and a neutron star. And you can actually calculate or measure the decay of the orbit in that binary and contrast this with the predictions of general relativity, assuming that there is energy being radiated away via gravitational waves. And indeed, the orbital decay of the Hulse-Taylor binary did match to very good precision the predictions of general relativity. So this was indirect evidence of gravitational waves, but that wasn't enough for most people. So LIGO planning began in the early 90s. Just checking the chat. Where people started thinking seriously about direct detection. And of course, that rest is history. The first detection was in 2015. And following that, complementary observations by Virgo, GEO 600, CAGRA, etc., have confirmed gravitational wave detections. And so far, around 100 gravitational wave signals have been detected so far. Right. Okay, so the basics of gravitational waves. We've all seen this in yesterday's lectures, so I'll skip through it really quickly. Gravitational waves stretch and squeeze space-time. They create transverse ripples with two polarizations. So in the picture on the right here, we can see the plus and cross polarizations, where you're sort of stretching along this horizontal and vertical axis. And then in the cross polarization, you're stretching along this axis, which is 45 degrees relative to the plus polarization. And the direction of propagation of the wave is into the page. So any time varying massive asymmetric system can generate gravitational waves. And we note that this requires a quadrupole. So not the monopole gravitational radiation that Einstein originally thought might be the case. But most are far too tiny to observe. So things like the Earth orbiting the sun, or other planets orbiting the sun, all of those sorts of phenomena don't generate gravitational waves that are within our ability to detect. So we need cataclysmic events such as merging compact binaries, so black holes, or neutron star mergers, that sort of thing. Extreme mass ratio in spirals, which we heard about yesterday, or things like supermassive black hole mergers, which are sort of energetic enough that they can generate observable signals. Gravitational wave detection provides a very strong test of general relativity and can be used to study the properties of black holes and distinguish between different cosmological models. So this is why we're so interested in developing detectors for gravitational waves. The basic principle that we use for gravitational wave detection is the interferometer. And as was explained yesterday, you essentially fire a coherent source of light from the left-hand side of the left image towards this beam splitter. It gets split along two paths. And if there is a relative change in the path length along those two paths, then when the beam of light is reflected back and recombined, you will get a characteristic interference pattern. So in the left-hand image, the recombined beam is interfering constructively. So you get this increase in the amplitude at the detector. And in the right-hand image, the beam is interfering destructively, so you get a decrease in the amplitude detected at the detector. So one thing that's important to note is that the arms don't need to be in right angles to one another. All you need is some angular separation so that there will be, if there is a gravitational wave passing through, that there will be a differential change in the path length between the arms. However, the sensitivity of the detector depends on the direction of the propagation of the wave. So you can imagine that if there was a wave propagating sort of vertically up the page, then the transverse modes would be oscillating horizontally as far as this diagram is concerned, and you would have one mirror that was moving and one mirror that was completely stationary. And so in this case, you would be able to get a decent sensitivity because you were getting a maximal sort of path difference change along the two arms. So even then, the path differences that we're talking about, the characteristic strain of a gravitational wave signal is parts in 10 to the 20. So that's a really, really tiny thing to measure and very difficult indeed to do so. And the characteristic strain of parts in 10 to the 20 corresponds to a delta L, or physical change in path length, of the arms of a detector like LIGO, which are about 4 kilometers long, corresponds to about 10 to the minus 18 meters in physical distance of a physical change in the path length. And just to put that into perspective, a human hair is about 10 to the minus 4 meters in diameter, and an atom is of order 10 to the minus 10 meters in diameter. So we're talking orders and orders of magnitude smaller than the size of an atom that we're trying to detect there. And so we heard yesterday about all of the things that make that extremely hard and all of the sources of noise that can interfere with the signal collection. So ground-based detectors suffer from a number of challenges. One of them is that they can only detect high frequency signals. So we're talking about 10 hertz to 10 kilohertz, which correspond to mergers of objects, which are about of order 10 times the mass of the sun. Below 10 hertz, there is a significant displacement noise from seismic activity. And that's really something that you can't escape anywhere on the Earth. The Earth is a very active planet, and it's always wobbling and groaning. So there's nowhere you can go to escape that, unfortunately. Then we heard also about vertical suspension resonances. So these big suspension structures that they hang the mirrors from in the ground-based detectors can sort of spin up and become excited and resonate, and that can cause issues in the noise characteristics of the detector. There's also vibrations in the building from even the tiniest things like humans walking around, wind outside, all of that sort of stuff. And you can't isolate from that. You can't isolate your facility from that, so you have to isolate your mirrors, and that's all very difficult. Then also there are fluctuations in the local gravitational field, tidal effects from the moon moving around the Earth, that sort of thing. And this can also couple to the gravitational wave channel and affect your results. Then the final sort of limitation of ground-based detection is that you have a limited arm length. The Earth is only so big, it has a curved surface, and in order to have a detector with straight arms, you need to somehow stay within the radius of curvature of this surface of the Earth. And that just limits your arm length of order sort of 10 kilometers. So despite all of these challenges, it's worth mentioning that ground-based detection has had huge successes. And on the left-hand side here, I'm just showing the sort of famous initial detection with LIGO, Hanford, and Livingston data, and showing the combination of those signals, and that they correspond very well to each other, and that is a successful detection. And then on the right-hand side, we've got a whole catalogue of detected gravitational waves from various different binaries within the galaxy. So this has been a huge success, but we want to go further. One way to go further is obviously improving the sensitivity of existing ground-based detectors. So there are upgrades ongoing for the LIGO Virgo detectors, and they're expected to reach design sensitivity in the next few years. And there are all sorts of ways that you can do that, like new mirror coatings to reduce coating-related noise and that sort of thing. Then there are the third generation ground-based detectors, such as the Einstein telescope and the Cosmic Explorer. Both of these have much longer arms than the LIGO detector, for example, but still on the order of 10 kilometers. It's worth noting that the proposed Einstein telescope is a triangular shape, a triangular detector, rather than the traditional L shape. And we'll get back to that shortly in the context of LISA. So these are some ways to improve ground-based detection. But what we really want to do is move to space-based detection. And there are two really primary reasons for that. The first reason is that the low frequency ranges, which are inaccessible to ground-based interferometers due to local gravitational noise and seismic activity, are accessible to space-based interferometers. They're completely isolated from any kind of seismic activity, since they're nowhere near the surface of the Earth. And all sort of human activity, wind, that sort of thing, they're also shielded from. So you can access these low frequency ranges that are inaccessible to ground-based detectors. The other thing that you can do is increase the length of your arms far beyond what you can do on the Earth. So longer arms correspond to larger absolute changes in the path length, meaning that you can detect weaker sources from much further away, and that the signals of closer sources will be a lot stronger as well. So those are the sort of primary motivations. And if we look at the figure on the right-hand side, you see that space interferometers sort of sit in this frequency range, or in this case, they've got a sort of wave period range, where you can look at things like, as well as compact binaries in our galaxy, also extreme mass ratio in spirals, binary supermassive black hole mergers, and also early universe sources as well. So it opens up a whole new window, sort of complementary to the window of ground-based detectors. So there's where LISA comes in. So LISA stands for the Laser Interferometer Space Antenna. It's a European Space Agency-led collaboration with contributions from NASA and many research institutions around the world, which are collectively known as the LISA Consortium. The aim of LISA is to detect gravitational wave sources with much larger masses than what has previously been detected, so such as massive black holes in the centers of galaxies, which will produce frequency signals in the 0.1 millihertz to 100 millihertz range. LISA will complement traditional electromagnetic observations, but can also observe objects that are shielded from electromagnetic observations by other stars or dust. So this is an example of this new emerging field of multi-messenger astronomy, where you can confirm your observations from one method or another with a completely complementary method. So using electromagnetism and gravitational waves is a really great example of that. So what is the sort of proposed structure of this mission? Well, LISA is intended to follow a heliocentric orbit. It's a constellation of 3 spacecraft trailing the Earth by about 20 degrees. So it has the same orbital period as the Earth, but it's got these 3 separate spacecraft, and they're all on orbits which are slightly inclined to the plane of the Earth's orbit. So in the lower half of this image on the right-hand side, you can see this gray line that traces through one of the dots of this triangle, which represents one of the spacecraft. And you see that at the right-hand side of the image, it's sort of above the Earth's orbit, or the ecliptic there. And then as you travel further around the orbit, it starts to dip below and eventually goes right below the Earth's orbital plane until it comes back up again the next year. So what this means is that each of the 3 spacecraft are on these slightly tilted and all tilted differently orbits, so that over the course of the year, this whole configuration appears to rotate. The plane of this triangle, of this equilateral triangle, is 60 degrees with respect to the ecliptic. And as I mentioned, it then sort of, this whole thing rotates, or the locations of the 3 spacecraft relative to the Earth appear to rotate throughout the course of the year. This rotation actually turns out to be beneficial because it allows for source location analysis. Between each of these 3 spacecraft, which are separated by about 2.5 million kilometers, there is a laser beam, which then forms this sort of triple Michelson interferometer configuration. All right. So why should we want this triangular configuration? What are the advantages of it? Well, first of all, 3 independent interferometric combinations of light travel time are possible, which means that the combination of the signals in the data processing stage allows for the synthesis of 2 distinct virtual Michelson interferometers, plus a 3rd null stream configuration. So the null stream is a linear combination of the data from the different interferometric combinations, which is where the combination is chosen specifically so that any gravitational wave signal will cancel, and all you're left with is essentially the signal from the noise. So any signal which is present in the null stream as well as the standard detector output can be discarded as noise. So that's a very useful way of cleaning your signal up, and is possible with this triangular configuration. The null stream also constrains source location. So the way that the linear combination is chosen in order to create the null stream relies on a computation of or an optimization over the source sky location. So it actually constrains the source location with a 2-fold degeneracy across the plane of the detector. But if the source is a long duration signal, which extends for sort of weeks or months, so that the detector itself moves appreciably within the Earth's orbit over that course of time, then you can remove this degeneracy and calculate a very good prediction of the source location. Another advantage of the triangular configuration is that any single Michelson interferometer provides maximal sensitivity to one specific polarization. And in general, gravitational waves will not arrive at the detector in its optimal polarization. So if you have two independent interferometers, then this allows for simultaneous measurement of the two polarizations, which is important to fully resolve the geometry of a source. And finally, another advantage of this triangular configuration is that the third sort of null stream configuration can also be co-opted so that you can provide redundancy if one of the sort of three streams had to go down for whatever reason. So because you can reconstruct the signal of one of the detectors from the other two, you have this redundancy built in, which means that maintenance could be performed sequentially on each of the different systems without interrupting data collection. So a little bit about the technicalities of the spacecraft themselves. So each of these three spacecraft rather, contain this LISA technology package, or LTP. And in the LTP, you have two gold platinum cubes, which are enclosed in vacuum containers. During launch, they'll be fixed by this launch lock mechanism, but will eventually be released once in orbit with high position accuracy up to down to 60 micrometers and a speed less than 5 micrometers per second, so that once they're there, free floating, the electrostatic suspension system can take over and position them perfectly within these sort of cubic housings. Then between these two things is an optical bench interferometer, which measures the position and orientation of the test masses. This information is then passed to a drag-free attitude and control system. So in drag-free operation, when these spacecraft are in their correct orbital locations, you essentially have these two gold cubes free falling, which means that they're completely isolated from any instrumental noise throughout the rest of the spacecraft. And then what happens is the DFACS, or drag-free and attitude control system, computes their position and uses micro thrusters to readjust the position of the spacecraft around the cubes themselves. So the cubes can be completely isolated and the spacecraft sort of adjusts itself around them. And this means that they can be used as the mirrors for the ends of the interferometer. So just to sort of contrast that with what was talked about yesterday, in the talk about ground-based detectors, we learnt about these very complicated suspension rigs that the mirrors are attached to in ground-based detectors, and that they have their own problems, and that resonances can start to develop in these suspension mechanisms. And so if you contrast the sort of the behemoth on the right-hand side with this really simple idea on the left-hand side, where you just have this free-floating cube, which is not attached to anything, you really can see how you can suppress noise to a great degree here. So it's worth mentioning that these little cubes are very small, so only about 46 millimeters across and weigh each about 2 kilograms. Okay, so those were the test masses, but there are also the lasers. So the lasers on each spacecraft are 2-watt near-infrared lasers, and they operate in a transponder mode. So this is because when a beam is sent from one spacecraft to another, the divergence over several million kilometers rules out passive reflection for the return path. So that's rules out the sort of same mechanism that is used in LIGO. That's an interesting question. I'll come back to that in the end. So it's unable to use the same sort of reflection mechanism in LIGO. So instead what happens is that the laser in the distant spacecraft gets phase locked to an incoming beam and then returns a high power phase replica. So when that phase replica beam returns to the original spacecraft, it's compared against the local laser, and then the change in optical path length is determined. And this tends to be in the range of 10 to the minus 12 to 10 to the minus 9 meters at millihertz observing frequencies. So one might be concerned with distance variations caused by the movement of different gravitational bodies in the solar system. And indeed, that is something worth considering. However, the great thing is that the distance variations caused by these sorts of changes in the solar system are much, much bigger, of order 10 to the 7 meters, but occur on much longer timescales, so they can sort of easily be separated out from the signals. On the right-hand side, I've just got an image of the laser construction, which was a part of this, a part of the LPT developed by NASA. So quite a small thing, like about half the size of a shoebox, and contrasts quite sharply with the large arrangements that one has in places like LIGO and Virgo. Oops. Okay, so just a couple more things. The image on the right is just to show how messy this whole thing, how complicated the whole thing gets when you're considering all of the other control mechanisms that need to go into it. So there are things like, although you've completely isolated your cubes from accelerations due to noise in the spacecraft and that sort of thing, you still have issues with cosmic rays and solar flares and that sort of thing, which which can significantly charge the test masses. And if they become charged, this can lead to corruption of the measurements by the inertial sensor, which is a capacitance sensor. And so what needs to happen is that occasionally at regular intervals, a charge management system, which comprises fiber-coupled UV lamps, has to discharge the test mass. And so when you build in all of these different little components here, you end up with quite a complicated but very compact payload. Another thing is that the test masses have to be coated very carefully to prevent disturbance from surface effects. And this is the same sort of thing that ground-based detectors also suffer from. But there are a lot of considerations here. I won't go into the details of many of them, but it's a very sort of sophisticated piece of machinery. Right, so what sort of signals are we looking for? What are these low frequency gravitational wave signals? Well, one source is massive black hole mergers in galaxies at all distances. So these massive black holes are from 10 to the 3 to 10 to the 7 solar masses. And we expect them all the way up to very high redshift at the sort of onset of galaxy formation. We also expect to be able to see massive black holes accreting smaller objects. So this is the extreme mass ratio in spiral type of event. We also expect to see close binary compact stars and stellar remnants already observed in the electromagnetic range, and that some of these binaries within the galaxy could also then be detected subsequently by ground-based detectors when they enter the frequency band corresponding to ground-based detectors. So this therefore will provide a very complementary set of data, but also we'll be able to see things like resolvable galactic white dwarf binaries, which the ground-based detectors are unable to observe. So that's in the pale blue in this diagram. We also expect to be able to see backgrounds and bursts from other possible sources, including these sort of exotic relics of the extremely early universe, such as primordial black holes. Now. Right, so why do we want to look at these things? So the science objectives for the LISA mission are as follows. The first is to study the formation and evolution of compact binaries in the Milky Way. So we would like to determine the spatial distribution of these binaries and improve our understanding of white dwarfs, their masses, their interactions and binaries, and enable combined gravitational wave and electromagnetic observations. So that's the multi-messenger astronomy that I was talking about before. We'd also like to study the origin, growth, and merger history of massive black holes across cosmic ages. So one thing we want to do is search for a population of seed black holes at early epochs. A lot of sort of galactic halo models require a population of seed black holes, and they vary widely in their assumptions made there. So if we can find some kind of observational constraints on how we should seed those models, that would be very useful in structure formation simulations. We would like to search the first galaxies through observations of intermediate mass black hole captures, determine the relative importance of different black hole growth mechanisms as a function of redshift, and just generally trace the merger history of galaxies from redshifts of about 30 up to the modern day. We'd also like to probe the dynamics at the centers of galaxies using extreme mass ratio inspirals. So we'd like to characterize the immediate environment of massive black holes in galaxies below redshift of 1 and the galactic nuclei. That's traditionally very hard to look at in the electromagnetic range because it's screened by a lot of other stars and dust and all sorts of things blocking views of the center of galaxies. And we'd like to improve our understanding of stars and gas in the vicinity of galactic black holes using, again, coordinated gravitational electromagnetic observations where possible. We'd like to understand the astrophysics of stellar origin black holes. And because LISA can resolve hopefully thousands of stellar origin black hole binaries, some of these will cross into the LIGO band weeks to months later as their orbits decay and they become faster and faster and higher frequency and then enter the LIGO band. So you can this enables multi-band gravitational wave astronomy and is a nice way to tie in the space-based observatories with ground-based observatories. We'd also like to explore the fundamental nature of gravity in black holes. So detecting gravitational waves directly and measuring their properties precisely to constrain general relativity, and also test whether the central massive objects in galactic nuclei are indeed black holes or some other kind of compact object that we don't quite understand, and then make precision tests of dynamical strong field gravity. We'd also like to probe the expansion rate of the universe, so study the expansion history, geometry, and dark energy component using precise gravitationally calibrated distances in cases where redshifts are measured. So in light of the sort of Hubble tension of late, this is a particularly useful thing that LISA would be able to offer as an independent measure of the expansion rate. And finally, we'd like to understand the stochastic gravitational wave backgrounds and their implications for early universe particle physics, and potentially the possibility of any unmodeled signals as well. So it's a pretty broad set of science objectives, and it's obviously a very versatile instrument, which will hopefully increase our knowledge of gravitational wave astrophysics immensely. So where are we with it? Well, the Pathfinder mission was launched successfully in 2015. It traveled to 1.5 million kilometers from Earth at the Lagrange point 1. And it was just a single unit which tested the release of test masses into near perfect gravitational freefall and tested the micronewton thruster system for the spacecraft control around those test masses. And the results were surpassed everybody's expectations and achieved a relative acceleration lower than 10 to the minus 16 compared to Earth's gravitational acceleration. So this is well within the bounds that are required for the sensitivity of LISA. And so this Pathfinder mission was a great success, and essentially all of the technology is there and it's sort of ready to go when funding and bureaucracy catches up, I suppose. So here's a more detailed timeline. And where we are right now is this blue dot, so the refinement phase. The Pathfinder was 2015. The current launch date is somewhere around 2035. And here's the sort of latest update. So in May 2022, the LISA mission passed the comprehensive mission formulation review, which means that it can enter the next phase of development. So this means that no critical issues were identified, and LISA was confirmed to have successfully reached a maturity sufficient to proceed to the next stage of development. So the next stage of the development is this phase B1 in the blue here, which is essentially the refinement phase, and focuses on the more detailed design work prior to launch. So all systems are go at the moment, but it's still quite a long time ahead. As with any sort of space-based mission, there's a big waiting period. But in the meantime, while we're waiting for the spacecraft to actually go up, there are plenty of papers. Nobody's sitting around twiddling their thumbs. Everybody's making all sorts of predictions and refining the tools that we might use, such as the tools for statistical analysis of the signals. So there are a number of research papers being published in anticipation of this mission, and there's just a list of a few of them on the right-hand side there. And I'd point out that this one is one of Renata's. The nominal mission duration is of 4 years, so there's plenty of time to capture data, and the capacity is up to 10 years. So it's likely that it will go for longer than 4 years of almost constant observation. So what are we doing in New Zealand to contribute to this? Well, in New Zealand, we've formed this group called the New Zealand Gravity Group, and this is who's responsible for this workshop. This is a large interdisciplinary team, which brings together expertise in mathematics, computer science, machine learning, astrophysics, cosmology, numerical relativity, and statistics. Some of the things that various members of this team are working on are, for example, the statistical challenges of gravitational wave signal extraction from raw data, and that's sort of Renata's area of expertise. Implications of early universe cosmologies and alternative dark matter models on expected LISA signals, and that's somewhere where Richard and my group sort of focuses. Frank has also done a lot of work on this. We've also got a focus on numerical challenges of modeling physics in the strong gravity regime. So that's where Jörg and Chris focused. Gravitational wave spectral synthesis for galactic binaries. That's where Jan and her students focus. And we've also got some capacity in applying deep learning techniques to identify visual and temporal patterns embedded with gravitational wave signals. And Matt Edwards is sort of focused in that area. So here's just a list of some recent publications. We've got one about gravitational wave spectral synthesis by Jan and her student Wouter. We've got one by Jörg and Chris on some numerical relativity applications. We've got one by Matt utilizing deep learning techniques to classify equations of state from rotating core collapse gravitational waves. And we have a sort of more cosmology-based one, stochastic gravitational waves from post-inflationary structure formation, and also the sort of core of everything, which is the statistics. A paper here by Renata talking about parameter estimation. So there's tons of work going on, and you can have a look at all of these papers on the New Zealand Gravity Group's webpage, which I provide a link for at the end. But just one final point is that there are all sorts of other opportunities for contribution, in particular in the context of multi-messenger astronomy. So the University of Auckland is also part of the LSST project, and it's possible that massive black hole mergers detected by LISA could be visible to things like the Square Kilometre Array and the LSST. So there are opportunities there. Then there's also opportunities in data processing, computer science, that sort of thing. The timeline for the whole LISA mission is a couple of decades, so there are plenty more opportunities to come and different ways to get involved. So just a very broad summary, some key numbers. The mission duration is 4 years planned and up to 10 if it's extended. The frequency range we're looking at is 0.1 millihertz to 100 millihertz. We'll be able to use this to hear rather than see in electromagnetic sense beyond redshift of 20, which is further than we can get with electromagnetic observations. We'll generate about 350 megabytes of data per day. So that's not actually a huge amount, but it's just, but it's such rich data. And because it's generating this every day on an almost constant observational run, we'll end up with a very comprehensive array of observations. The sort of path lengths that we're talking about are between 10 to the minus 12 meters and 10 to the minus 9 meters. So still smaller than the size of an atom, but a great improvement on what you can get with ground-based detectors. We expect to be able to see about 10,000 galactic binaries during the 4-year duration of the LISA mission, some of which will then enter the frequency bands of ground-based detectors. So we will have multi-band gravitational wave observations there as well. And then finally, the arm length is about 2.5 million kilometers, so a very large constellation that we're talking about. So this is going to be the first ever space-based gravitational wave detector. It opens the door to a much richer frequency band than Earth-based detectors are able to achieve. Much work has already gone into it. The Pathfinder mission was a great success, and the full mission launch is planned within about 10 years. There's plenty of opportunities for new science, and the New Zealand Gravity Group is sort of spearheading that and as part of the global LISA consortium. And you can find out more information at these 2 websites here. Cool, I'll stop there.
Awesome. Thank you, Emily. And there's a couple of questions in the chat, one of which, all of which may be sort of like open-ended questions about how this is done. One of which is very much going to be a focus for our statisticians. Emily, do you want to get to bat at any of those, or and does anybody have any other questions for Emily before we roll into the next talk?
What have we got? So, is there a reason why one chooses cubes and not spheres, say? That is a really good question, and I would imagine it makes it easier to, well, first of all, I don't know how precise you can be with where the incoming signal is going to sort of land on the face of the mirror. And so you'd want a flat surface so that it's sort of striking at the same angle in any case. It might also be a case of it being easier to then dynamically adjust the positions of the test masses, but I'm not actually sure about that. Is there any concern about gravitational wave sources interfering with each other? So there will definitely be gravitational wave sources interfering with each other. And there's a huge sort of field, and Renata, or one of the statisticians, is probably best placed to comment on how you can sort of extract different signals from a highly mixed up overall signal, and how you can characterize stochastic backgrounds and that sort of thing. So there is a huge field of study looking into that. So yep, it's definitely a cause for concern, and extracting those individual signals is an active field of research. Did LISA Pathfinder also test the UV system to remove charge from the test mass? I don't know. I would assume yes, but I haven't actually read anything about that. But I can look it up in the data and the Pathfinder stuff and get back to you. You have mentioned solar flares and cosmic rays. What other sources of noise are there for LISA? How do they compare with the ones for foreground-based detectors, as in amplitudes? Well, so because the instruments themselves are all completely isolated from the test masses, they really are sort of isolated from all sorts of noise that you would expect in a ground-based detector. But you do have noise from things like random gravitational perturbations that you might not predict. The solar system is an active place and lots of things are moving around. In general, the planets and things move in a predictable orbit. And as I said before, those can be extracted, the implications of those can be extracted from the signals because they're generally on much longer time scales. But then you're still going to have the noise from things like photon shot noise and the noise associated with the lasers. And those will be comparable to the same noise sources in ground-based detectors. But you can go on the LISA website and you can look up the big figures which have all of the different noise sources and the sensitivity corresponding to each of those noise sources for more information there.
Cool. Awesome. That is a fantastic talk. So let's virtually or with our microphones off and our thumbs up, thank Emily for that presentation. And the next talk I want to call on Susan Scott, who's going to tell us about binary merger events. And hopefully Sue is there, and hopefully her computer is working.
Okay.
You just popped up at the bottom right corner of my screen. It's always a bit unnerving, these things.
I'm just going to try to share my screen.
Yeah, it should be able to. Welcome to Auckland. Welcome back. Nice to see
Thank
you
you.
again.
Just got to find the right file. We've got a bit of time.
We do, in fact, yes.
Susan, should I come down to your room?
Oh, it's okay. Let's see how I go with this.
Hey, you got it. You got it.
Is that shared properly?
It is. It is.
Okay, that's very good to hear.
Awesome funnel diagram.
Yeah, I might just stop for a moment because I think I forgot to turn my video on.
Yeah, we can see your screen, but we can't see.
I can see you,
and we can hear you. But it looks like something's happening.
Yeah.
And now we can see and hear you. This is awesome.
Yeah, you haven't got my file. That's the other thing.
Yeah, or we can. I mean, you should be able to share screen, I think, as well as camera.
Yeah. I should be able to. I'm just going to find.
Also, you win the prize for best background.
Thank you. I can't claim credit for it though.
Well, I haven't seen Roy's cat yet. He there's also a prize for the best feline intervention.
Hello, Roy. By the way, I will suitably give you a plug in our my talk today. Just forewarning. Can you see that? Okay.
We can, and I think if you just present, I think we'll see you. We'll see it.
Very good.
Well, however you want to do it.
Yes. Well, okay. Whenever you're ready, I can begin.
Okay. I'm going to forget many of your accomplishments when I do this because I'm speaking without notes. But it's a real pleasure to have Susan participating in this workshop. Susan, as I believe, are you the director of Osgrav in this incarnation?
No, I am not. I'm a chief investigator.
Chief investigator of Osgrav, which is our much larger Australian cousin, which has recently been funded as an ARC centre heading into the future. And so we're looking forward to interactions around that. But one of the world's leading gravitational physicists and relativists who's done, as huge career. And undoubtedly very interesting things to tell us today. So take it away.
Okay, well, thank you for that introduction, Richard. So, first of all, thank you to Jörg and Richard and all the other colleagues who've organised this summer school. I think it's such an important thing for New Zealand postgraduate students to get an overview of our field, because, to be honest, this is a really happening field and has been now for a decade or so. Obviously, there were things happening before that, but it's blossomed since 2015. And today I want to give you an overview that ties together everything you're hearing in the other lectures, which the ones I've been to so far have all been fantastic and very informative and giving greater details about particular parts. There'll be a little bit of overlap with some of them, but not a lot. So really this story of what we're doing today is a 100-year story. And that's what I'm going to tell you about and how it all fits together. And I want to motivate it by this very short video, which was made in 2014 by one of the members of our collaboration. And as many of you will know, that was the year before we actually achieved the first direct detection of gravitational waves. And I think it really conveys the spirit of the collaboration during all those years when we had nothing, which were leading up to detection. So I'll play that now, if I can.
Gravitational waves have never been detected. We're literally creating a new branch of astrophysics right now. Gravitational waves are the sounds of the universe. Up until now, we've been deaf to what's happening in the universe, and we're about to turn on our ears. Once we started looking up at the sky with telescopes, we didn't stop doing it. We're never going to stop listening for gravitational waves. Just working, okay. So that is the motivator for the talk, if you like. But in a sense, a motivation for the whole thing has been binary mergers, which is going to be eventually what I talk about today at a certain level, and Avi will talk about it in greater detail tomorrow, so stay tuned for that. So I should acknowledge that I'm based at the ANU Centre for Gravitational Astrophysics at the ANU in Australia. I'm a member of the LIGO Scientific Collaboration, which I joined at its beginning in about 1997, so long-standing member of that. And of course, we have this wonderful Centre of Excellence for Gravitational Wave Discovery called OzGrav, which is a national-wide thing in Australia that you've heard about. And before I start talking, I should shamelessly encourage any students who wish to join us in Australia. for postgraduate studies in anything to do with ground-based detectors, you are very welcome. And at ANU in particular at the moment, we're seeking to have new students in instrumental science. We have a very big program of that at ANU. I'm not part of that program. I'm a data analysis theory kind of person, but you're certainly very encouraged to apply to work with us if you wish. So this 100-year story, of course, and everybody's mentioned him just about so far, starts with Albert Einstein, arguably the most famous theoretical physicist ever. And in your undergraduate studies, you've no doubt seen a number of his contributions, important contributions, the photoelectric effect, Brownian motion, special relativity, which we've heard about a bit today as well, the equivalence of mass and energy, E equals mc squared. But I like to think Albert's greatest contribution was that of his general theory of relativity. And that's what we're talking about today. So although the paper may have appeared in early 1916, I believe the theory was actually presented in 1915. So that's the date we're working off from the start of this 100-year period. And basically his idea is that we have a unified description of gravity as a geometric property of space and time, which we call space-time. And space-time is what it's all about. And this is encapsulated by the Einstein field equation, which you have seen in the general relativity sections here. You've seen it in Jörg's talk and so on. But on the left-hand side, we have the geometry of the space-time encoded. And on the right-hand side, we have the mass and energy content of space-time encoded. And this field equation beautifully gives a symbiotic relationship between those two things. And the idea is that when we have matter in space-time, it actually warps space-time. Now, we saw this famous quote by the very eminent American physicist John Wheeler in Jörg's talk yesterday. And it starts saying, matter tells space-time how to curve. So here we've placed the Earth and its moon in space-time. And the Earth is 81 times more massive than its moon. So it actually dents space-time more, much more, and therefore it gives greater curvature to the space-time. And it's actually this curvature that we perceive as gravity. So we have the masses denting space-time, curving it, and on the other hand, space-time reacts back on matter, telling it how to move. So if we placed an observer somewhere between the moon and the Earth, then the space-time would tell that observer how to move. Okay, so there are two big themes here in this 100-year history leading up to gravitational wave detection. And although there was quite a lot of advances in general relativity theory, which happened in those 100 years, these are, I think, the two most important themes. And obviously, they come from Albert Einstein, but they come together again later in this 100-year period. So the first one starts with Karl Schwarzschild. And again, Jörg mentioned him this morning. And he was a German astrophysicist and signed up for the German army, I guess in 1915, and was stationed on the Eastern Front in Russia as a minor officer, let's say. And Karl, being an astrophysicist, wanted a very practical approach to dealing with Einstein's field equation. So he set himself the following task, and that was to find the solution to the field equation for the gravitational field outside of a non-rotating spherically symmetric star. So as I said, this is a very practical problem that an astrophysicist at the time would like to know the answer to. So one can only imagine that Karl was, fighting by day and in his little officer tent by night with, a kerosene lamp or something, beavering away, trying to find a solution to the field equation for this problem. And he did, to his credit, and we call this the Schwarzschild metric, as you've already seen. So in spherical polar coordinates, with coordinates t, r, theta, phi, this is the beautifully simple diagonal form of that metric. And we can see, and I feel certain that Carl saw this himself, but we have a bit of a problem when 1 minus 2m on r equals 0, which is when the radius is 2m in geometric units. So clearly the metric in these coordinates looks singular at r equals 2m. So it's a problem. But of course, Carl didn't imagine this was a problem at all, because he was finding the field outside of a star. And at that time, every star that people knew about had a surface radius of much greater than r equals 2m. So this wasn't, I guess, an issue from his point of view. And his metric, his solution, was taken back to Germany, and I believe presented by Einstein to the Prussian Academy of Sciences. And I think this also happened in 1915. So further advances in this direction were by Oppenheimer and Snyder in around 1939, and they were considering the idea of, if you like, gravitational or stellar collapse of sufficiently large stars. So the idea is that the sun and other stars are held in balance between gravitational self-attraction and the pressure of thermonuclear reaction. So they're sort of propped up by that. But eventually they burn up all their fuel, and then they explode as something like a supernova. And then they undergo gravitational collapse. And if they end up as something like less than 1.4 solar masses, they'll be what we call a white dwarf. Something in the order of 1.4 to 2 point something solar masses, a neutron star, and greater than 2 solar masses, possibly a black hole. Okay, well, going back to Carl's solution. So here we have the time radius representation. And you can sort of see what the problem is here, because we have that vertical surface at r equals 2m. And what's plotted are radial ingoing and outgoing null geodesics. And what you can see is that the null cones, which form between these null geodesics, are actually being squashed as we approach the surface r equals 2m. And at the same time, we see that they're approaching this surface with a time coordinate going infinite. And yet it was known that the proper time along these geodesics was actually finite. So clearly the representation wasn't ideal in some sense, and therefore this surface r equals 2m was still a kind of mystery, if you like. And we've heard again in the talks earlier today that this problem was tackled. And believe it or not, it took like 45 years from 1915 to 1960 for general relativity theorists to really understand what was going on at this surface r equals 2m. And here we have a picture of Sir Arthur Eddington on the left and David Finkelstein on the right, who came up with what now seems to be perhaps an obvious idea to approach this issue, and that is to use coordinates pinned, if you like, to these radial ingoing null geodesics as one new coordinate along with the remaining spherical polar coordinates. And this allowed the ingoing null geodesics to pass through that surface as they should do in finite proper time, and to regularize the metric across that surface. Finally, in that final piece of that story, in 1960, both Martin Kruskal, an American, and George Zekaras, an Australian originally from Hungary, came up with the maximal analytic extension of the Schwarzschild solution. And the original solution by Carl is the bit in the right-hand triangle. So that's the bit r greater than 2m. And then you have the horizon, and these geodesics will proceed through that horizon and reach this jagged surface at the top at r equals 0, which is the black hole, if you like. And this is a Penrose diagram, and invented by Roger Penrose, where all null cones are represented at 45 degrees. So these are very beautiful diagrams which can be used to depict certain spherically symmetric spacetimes. So this is, if you like, this is the ultimate representation of Karl Schwarzschild's black hole. Okay, well, dealing with that and allowing for stellar collapse, one can now, by this stage, think about allowing his solution to be valid all the way into the center of the star at r equals 0. And this is, of course, the black hole solution. So we have the event horizon at r equals 2m, and we have the singularity, if you like, at the center with infinite curvature. And nothing, at least classically, can escape from inside it. And now we come to the next big development, which was, of course, by Roy Kerr, New Zealander, as I'm sure all of you know, in 1963. Because sensationally, at that time, Roy found the solution for the rotating black hole solution. And of course, this was, Carl had found the non-rotating one, but Roy found the rotating one. And of course, this is very important because insofar as one might think there are black holes out there in the universe, of course, we would expect them to be rotating. So this was a very major development. And for this, Roy won the Craftford Prize in 2016, which was very well deserved. And this is the cover of a book by myself, David Wiltshire and Matt Visser, about the Kerr spacetime and many aspects of its properties and structure. So yes, this is a huge step forward. But also around this time in general relativity theory, people were really thinking about the issue of singularities in general. So you can imagine, like there's a singularity at the center of this black hole solution because the curvature is going infinite. So yeah, both the Schwarzschild solution and Kerr solution have singularities with infinite curvature. But up until this time, I think it was a feeling in the general relativity community, including from Einstein himself, that black holes and singularities would not actually exist in nature. And they thought that they were coming up in these solutions purely because of the high degree of symmetry, which is assumed to find these solutions. And don't forget that the Einstein field equation is fiendishly difficult to solve. And so obviously people do, at least initially, plug in a lot of symmetry to have any hope at all of solving them. And so this was the case for these two solutions. And thinking about it, when you look out in the universe at all the objects that people knew about out there at the time, there was nothing with absolute, high level of symmetry. Stars have flares and explosions, and neutron stars have little mountains and irregularities, and everything has imperfections. There's nothing like completely symmetric. So there was no reason in a sense to imagine that these solutions were physical. So the idea was that these singularities wouldn't occur in more general solutions. And I note here, and I think this is an accurate story, and I hope Roy would correct me if it's not, but Roy presented his solution to an audience made up mostly of astronomers at the Texas meeting of 1963. So remember, this was around the time of his solution. And I like to use this picture here because as I understand it, there wasn't an amazing reception from this astronomy part of the community about the solution. They thought that this so-called singularity was really absurd and clearly, indicated some kind of failure of Einstein's theory. And, that there must be some physical mechanism that occurs to prevent a star from collapsing that far. And I will say about this picture that I did include it in a talk recently to students, and somebody asked me about the picture and obviously thought it was real. And I must say, clearly is not, it's not real. All right, so continuing on, from the late 1950s, we have the emergence of someone called Roger Penrose. And his roots are as a pure mathematician, and he brought to general relativity new mathematics. So differential geometry, differential topology, and these were very powerful tools which he brought to bear on this very issue about singularities and, you know, whether they should be in general relativity theory or not. And in 1965, he produced his singularity theorem. So he was addressing the question of non-spherical collapse with this theorem. And this theorem is now 50 years after the birth of general relativity theory. So we're talking halfway through this 100-year period. So he was addressing the question of non-spherical collapse for precisely to address this question of whether all this symmetry assumed in these solutions was in fact the cause of these singularities. And he argued that any object with an event horizon, irrespective of its shape, will contain what he called a trap surface. So an example of that is, say, for a sphere, if we shine light from anywhere within or on the surface of the sphere in any direction, all the light will shine inward, and that is due to the very strong gravity occurring in that particular situation. So the implication from this is that anything inside a black hole has only one future, and that's falling further and further towards the center. And this process doesn't stop. It keeps on going until something catastrophic happens, and that is that the observer reaches the singularity. So this is a very, very powerful theorem. And to summarize it, what it says is that if you accept general relativity theory and you have sufficiently massive objects undergoing gravitational collapse, then you will get black holes irrespective of the shape or symmetry of the object. So this was a huge result, and you know, possibly one of the biggest results ever in the history of general relativity theory in many ways. Because it said that, you know, these special solutions, these important solutions found by Schwarzschild and Roy Kerr were not just really special cases due to the symmetry. That in fact, insofar as you accept general relativity theory, you will expect to have black holes. Now, Einstein predicted so many things from his own theory that there were very few things that we have thought about and talk about throughout the history of relativity that weren't predicted by him. But this is most certainly one of them. And he didn't really quite live to see the full evolution of this part of the story, but I expect he wouldn't have been very happy initially, but I like to think that one day he sort of would have come around and, you know, been more content with the situation. The singularity theorems continued throughout the 60s with Roger Penrose and Stephen Hawking, and they established that singularities are a general feature of space-time in general relativity. Every black hole contains a singularity, and every expanding universe begins in a Big Bang singularity. So together they formed a very powerful piece of work, and none of this was foreseen by Einstein. And very, very pleasing and wonderful to see that for his 1965 singularity theorem, Roger Penrose deservedly received half of the Nobel Prize for Physics in 2020. And it's just wonderful that Roger lived so long to actually have that happen. And I think the relativity community is very thrilled that that actually came to fruition. the story doesn't quite finish there. Also in the 1960s, there were studies of how many types of black holes we can actually have. And it turns out that we can have the 4 types: the non-charged, non-rotating Schwarzschild solution, the non-charged rotating Kerr solution, and then the charged versions of both of those 2 solutions. So the non-rotating one charged is Reisen-Nordstrom, and then the rotating and charged one is Kerr-Newman. So this was pretty amazing because, you know, the whole story had gone full cycle in the sense that, you know, people had believed that there were no, you know, totally symmetric objects in the universe and certainly didn't believe in black holes. But then the singularity theorem showed that we would expect black holes from general relativity theory. And then these powerful theorems about types of black holes showed that there were only these 4 highly symmetrical types. So in fact, there are highly symmetric objects out there in the universe. And if you like, black holes are a kind of geometric object. So this was a big deal because general relativity theorists had pretty much wrapped up the story of black holes by the 1960s. And this is totally the opposite way to how things normally work. Normally, astronomers go out there and they're observing all kinds of stuff, and then they find stuff that nobody knows what it is. And then everybody tries to figure out what's happened. Well, in this case, it was the other way around. GR theorists had the story about black holes pretty much sorted out. And it wasn't until 1972 that the first serious candidate for a black hole, Cygnus X1, was found in an X-ray binary system. So now the astronomers were on board. Okay, so just recapping here, Einstein's theory had very large, far-reaching consequences, many of which he predicted, describes the motions of the planets, the physics of black holes, the bending of light from distant stars and galaxies, and the history and expansion of the universe. And a couple of pictures. Here's the bending of light. And I was very fortunate last September to go to the 100th anniversary of the Whale expedition to view the solar eclipse where this bending of light was really confirmed. And that's an Einstein ring in the lower right-hand diagram. Okay, well, that's the first thread. And that now brings me to the second thread of this 100-year story. And this thread, of course, is about gravitational waves. And we will see just a little later how these 2 threads most beautifully come together. So Jörg yesterday showed excerpts from this original paper, which now actually the work, the initial work for this from the linearized theory, I believe Einstein did in 1915 again. So again, it was the same year. It's published a few months later in 1916. But this, you know, as we heard in the last talk, there was a bit of an evolution of Einstein's thinking about these gravitational waves. But this is the first time he published the fact that there should be gravitational waves coming from his own theory. But he said quite famously that in any case one can think of, the gravitational wave amplitude will have a practically vanishing value. Because at that time, Einstein didn't really know about cataclysmic enough events, perhaps out in the universe, which could produce things strong enough to produce detectable waves. But also this state of technology then was in a totally different regime to where it is now. There were no lasers, transistors, it wasn't quantum optics or pure mirrors. So there was really no way he could imagine that they would ever be detectable. And I'm not going to talk about electromagnetic waves because Jörg talked about them yesterday and you've all studied them. But, you know, at this point, throughout humanity, you know, much of our what we do as humans and how we've observed the universe up to that point was through the electromagnetic spectrum. And so this was what we used for most of our history of humanity. So gravitational waves, and I'm not going to go into this again because you've had quite a lot about it already, but it's a totally different type of wave and it forms a new spectrum. And they were predicted by Einstein, I think, strictly speaking, in 1915. And the idea is that whenever we have masses jiggling around in space, as long as there's a particular type of asymmetry, then they will produce a perturbation of space-time as gravitational waves, and these will move outwards from the source as distortions of the space-time, and they travel at the speed of light. It's very important, though, that they're in a different spectrum. They're not light waves, but similarly to light waves, they come in different wavelengths. And that's where, you know, we then think about having all these different types of gravitational wave detection experiments. And we heard about LISA in the last talk, which cover different parts of that spectrum and therefore receive waves from very different phenomena happening out in space. And this is great because we can learn so much from the universe through all these different detectors. So you've seen this before, but this is a ring of freely falling test particles. And we can imagine a gravitational wave traveling into the plane, and it will alternately stretch in one direction, and then in this case, the direction at 90 degrees. So we have this kind of effect on this ring of test particles, which can be imagined in the gravitational wave interferometers that we now use located on the Earth's surface. So here, and I'm not going to go through it, you've seen it various times, but perhaps I'll add here that, you know, we have these arm lengths, equal arm lengths of say 4 kilometers in the case of LIGO. And you can imagine a ring of test particles going around those two end mirrors at the ends of the two arms. And so the effect is the same, that as a gravitational wave passes through the plane there, it will stretch one arm and then alternately the other arm. And we get this interference pattern, which is at the photo detector and indicated in terms of light intensity. The amount the arms stretch, typically, it's equal to the gravitational wave strain amplitude, let's say 10 to the minus 21 for the sort of things we would expect by the length of the arm, so 1,000 meters. And we get an effect of a length difference of about 10 to the minus 18 meters, which is about 1,000th of the width of a proton. So here was the challenge. You know, once the idea of something to detect gravitational waves was hatched by Ray Weiss in the 1970s, you know, is how can we make this instrument sensitive enough eventually to detect such a very small change in distance? A couple of other properties which are worth mentioning. Here we've got a person with a sledgehammer on a railway track and a friend stationed quite a distance away along the track with his ear to the rail. Now, if this person with a sledgehammer gives it an almighty quick whack, then the other person will hear it very quickly. If he just sort of taps it with his finger, then the other person won't hear anything, of course. So this is a good analogy with gravitational waves, because a property that many people don't realize is that space-time is in fact very stiff. And so likewise, something very massive and moving at very high speed is needed to warp space-time and cause it to vibrate sufficiently to be heard a long way away, e.g. with us at planet Earth. And to put a figure on it, space-time is approximately 22 orders of magnitude stiffer than steel. So it really is very, very stiff. Another interesting property is that gravitational waves interact only weakly with matter. And that is, of course, why they're incredibly difficult to detect. But the plus side is that they basically travel freely throughout the whole universe, unhindered and unaffected. And this is very different to electromagnetic radiation, as every astronomer knows. There's problems with light signals being absorbed and scattered by intergalactic dust and all kinds of stuff. But gravitational waves arrive and should arrive at Earth pretty much pristine. And indeed, we can detect them coming from the other side of the Earth. They can travel through the Earth. They can travel to our detectors in any direction, pretty much pristine. Okay, well, during all this early period of thinking about gravitational wave detectors and so on, there was a growing corroboration, if you like, that gravitational waves actually existed. And you've seen this plot before, which I believe Jörg put up yesterday. Okay, so this was a binary pulsar system discovered by Holson Taylor in 1974. So basically 2 neutron stars in a binary system, which are both radiating electromagnetically. And the idea was that as they orbit, they're going to be emitting radiation and energy in the form of gravitational waves. And this will cause their orbit to shrink. And it can be predicted very precisely by general relativity theory. And this is the curve you see on the diagram on the right. So the vertical axis is the deviation in time of orbit from the initial observation of the system. From 1975, the horizontal timeline, to 1993. And the predicted decrease in orbital time really precisely matches the observed data points. And this was a beautiful corroboration, if you like, of the indirect evidence of the existence of gravitational radiation. And for this, they were awarded the 1993 Nobel Prize in physics. So this brings us to the LIGO detectors. The initial proposal to build these detectors wasn't until 1989. And proposal was put to the United States National Science Foundation. And it was very clear already, you know, the long journey ahead should this be funded. If you read point 3, the first detection is most likely to occur not in the initial detector in the LIGO, but rather in a subsequent one as the sensitivity and frequency are improved, to paraphrase it. So everyone knew that it was going to be a long journey, and it wasn't clear exactly how long at that stage, but you know, it wasn't going to happen quickly. So that's an artist's impression on the left, and on the right is a Lego model of a LIGO detector. This is our 2 observatories today, one in Hanford in Washington State. That's the top left one. It's located in a desert in a Department of Energy kind of waste zone, if you like. And the bottom right one is in Louisiana in a kind of swamp. So in very different environments. They both have 4-kilometer arm length, as you've heard. And this is a map in the bottom left, which shows their location. So there's this very long baseline of over 3,000 kilometers between the 2. And that wasn't a coincidence, of course. Obviously, you know, with 2 of them, all the noise sources and so on in each detector can be looked at, and a signal, assuming largely the noise sources are different in the 2 detectors, then a signal should be able to be picked out from the data stream. It also gives, you know, a different arrival time of the signal. at the detectors, and the further apart they are, the more different the arrival time. And that helps us to determine where on the sky a signal comes from. So bear in mind that these detectors just sit on the Earth. You know, you don't point them, you don't do anything tangible to them in the sense of directionality, and they will just receive gravitational waves as they come through. And by having a network of these detectors, we will have time delays between all of them, which help with directionality. And also, I don't think it's been mentioned so far, but these detectors are weakly directional. And so with that information as well, it helps us with directionality of the signal coming in from the universe. And then currently also operational, we have the 3 kilometre arm length European detector called Virgo, located in Cascina in Italy, and also the Japanese detector Kagra, which is located under 1,000 meters of granite in Kamioka Mountain. And of course, that is important. Japan is very seismically active, which has a big effect on interferometers. And so they've put it under this mountain to mitigate that. But also it's cryogenically cooled, which is another advancement and improvement of eventually sensitivity. So we have 4 currently operational detectors, and one is due to be constructed in India called LIGO India. Okay, so in all these decades, there's a huge amount going on with the detectors, and there's technology constantly being developed by our significantly large team of both physicists, experimental physicists, and engineers. So all this is going on, and one might think, you know, what's happening with the theorists and data analysts and so on during all this period? Well, the fact is we were really, really busy with it all. You know, for a start, the LIGO data analysis system had to be built from scratch. So the data acquisition system, and then, you know, the basic processing of the data, how that was going to be done, the characterization of noise, of the amazing number of noise sources we have to deal with, the calibration of the detectors. But importantly, you know, if you're going to make a first detection, you want to have a prediction, a very good prediction of the signal. And so this is an area where there was a lot of work going on. So the question was, what would the gravitational wave signal look like from astrophysical and cosmic events? Well, the type of signal that LIGO had been designed for and had been built into all the documents when seeking funding to build them was for a binary neutron star in spiral. So we thought our most likely first detection would be from a binary neutron star in spiral. And so the work was going on to work out the signal from a binary in spiral system, which could be 2 neutron stars, or it could be 2 black holes, or it could be one of each. And this actually was a very difficult problem. And again, it took several decades of investigation, and we've heard a bit about this yesterday from Chris and so on. And it took numerous breakthroughs to produce the expected gravitational wave signal. And here's Kip Thorne's beautiful hand-drawn diagram in the top part of 2 black holes merging. So on the left, we had the in-spiral phase, and this was well known. So this part of the signal was fine. Then there's the merger phase where they actually coalesce. And then we have what we call the ring down phase, where the new black hole's been formed and it's ringing down to come to a sort of stable state. And this part of the signal was also pretty well known. So it was a bit in the middle that we didn't have well determined, but in a sense, this was the part we really wanted to know, because it's, you know, the part where the gravitational field is strongest and most dynamical, and the signal itself is going to be strongest in that point. So it's very important for us to fill in that major gap. Fortunately, after decades of struggle, in 2005, there were major breakthroughs in numerical relativity made independently and using different methods by 3 research groups, and one of them led by Franz Pretorius. And this was the breakthrough. Finally, we were able to calculate that really important coalescence part of the signal. The ring down phase, when the new black hole's formed, you can think of it as like a bell after it's been struck. So we've got these gravitational wave wiggles of the new black hole, and they can be studied analytically. And Chandrasekhar was an important person in that work. And of course, the final state, when it's all settled down, should be a Kerr black hole. Okay, well, this brings us to detection. Okay, so this 100-year story is now up, and the 2 themes have come together. We've got the black holes story and we've got the gravitational wave story. And on the 14th of September 2015, that story came together. So that evening I was at home in Canberra, and I got a text message saying Australia has a new Prime Minister. So I was just absorbing that. To be honest, we'd had several over the recent few years, so it wasn't all that kind of exciting or surprising. But as one would say, then something went bump in the night. And later that evening, I got an email from within the collaboration to a particular subgroup of LIGO, and it said, amongst other things, there has been a very interesting event in the LIGO detectors in the previous hour. And just to put this in perspective, we've talked about how there was this initial LIGO phase, and even in the funding proposal, we didn't expect to achieve detection in that phase because the instruments weren't sensitive enough to make it probable. And in fact, we did not make detection. So we've been down now for several years upgrading all the subcomponents of the LIGO detectors, and Virgo was doing the same. And we're in the final engineering run, and we're like 2 to 3 days out of starting the first ever observing run of advanced LIGO. So this is when all this happened. And, you know, events unfolded very quickly that evening, and by very late that night in Canberra, you know, it became pretty clear that this was in fact the real thing. And by that stage, it was very frustrating because I couldn't actually tell anyone, because first of all, the collaboration wasn't allowed to tell anyone. But secondly, the few people in Canberra who were in the collaboration had all gone to bed. And so I couldn't even tell them. So it was very, very frustrating, which is why I'm depicting there a sleepless but excited night. So what it was in the end, it was 2 black holes. It wasn't 2 neutron stars. And these are the 2 signals, the red ones from the Hanford Observatory and the blue one from the Livingston Observatory. And there was very, very good agreement between the 2 signals. And we like to play the signal that we received, because it's actually in the human audio band. It's obviously, our ears are much too insensitive to even think about hearing a signal of that magnitude, but this is played it is in the audio band, and we play it first at the actual frequencies, and then we shift it up to the kind of human hearing sweet spot. And as you'll hear, it's like a sort of chirp sound, we call it. And that's the classic in-spiral sound. So that signal is going up in frequency, corresponding to the 2 objects, the 2 black holes, are spinning faster and faster as they get towards coalescence, and the signal is becoming stronger as they approach coalescence. And you can see here the signal lasts for just a fraction of a second. So these are not very long. Here are the process waveforms of that event. And in the bottom one, the Hanford signal has been time shifted because there is a time difference in arrival slightly. And you can see that there's very good alignment of the two signals. Parameters for the system, solar mass, the black hole masses were about 36 and 29 solar masses, and the resultant black hole about 62. So the missing 3 solar masses are the energy radiated in gravitational waves, final spin of the resultant black hole about 0.67, distance 410 megaparsec, and the maximum power outputted during the event, of course, over a very short period of time, was equivalent to about 200 billion supernovae. So huge. Are these the black holes of general relativity? Well, the answer is yes, to the precision that we have measured that particular waveform. And in the bottom right-hand, in the bottom diagram there, what we have is, well, first of all, the time of the signal. So from about 0.3 to 0.45 seconds. Then in green, we've got the velocity of the two objects. And you can see that by the time, and the top curve is black hole separation, by the time we're getting down to like 1 Schwarzschild radius, which is where they're coalescing, the speed of the objects is, above about half the speed of light. So things are indeed moving very, very fast. These are extreme numbers. As I said, a collision converted 3 solar masses into an energy burst about equivalent to about 3,000 suns in their 10 billion year lifetimes. But that burst only lasted about 1/10 of a second. It's the rate of energy emission during that short period was about 50 times bigger than that from all the stars in the universe. But if you're only 10,000 kilometers, Sydney to Los Angeles, let's say, from the black hole collision, then it would have only stretched you by about 0.5 millimeter. And let's face it, that probably happens to most of us overnight while we're sleeping, something of that order. So LIGO did indeed measure a change in the length of each arm of the interferometer of about 10 to the minus 18 meters, which is equivalent to a change in the distance to Alpha Centauri by 10% of the thickness of a piece of paper. And Jörg showed this yesterday, but I'll just show you the beautiful simulation created by the SXS, I don't know how they pronounce it, collaboration. But you've got a background of a stellar background, and because of the change in symmetry going on with this black hole spiraling system, of course, from Einstein's deflection of light, you had those stars behind looking like they were sloshing around until we settled down to the final black hole. Okay, so just to give you an idea of the timing of all this, so the event happened 1.3 billion years ago, this binary black hole death spiral. At that time, we had complex multicellular life on Earth. About 8 million years ago, these gravitational waves entered the local group, which includes the Milky Way. And at that time, about that time, humans and chimps separated. Then about 100,000 years ago, the gravitational waves arrived at the Milky Way, our galaxy, and Homo sapiens arrived in the Middle East. And then the story I'm talking about today started about 100 years ago when we had this kind of genius present us with the general theory of relativity. So we had 100 years from that point to be in a position to detect those waves from that event, which had happened so much earlier. And we did. We got our act together and we built these giant objects. These are massively complex instruments which just sit there, and we were ready just in time to to detect this signal. And that resulted in this announcement paper, the first direct detection of gravitational waves, which was in February 2016. And here is our press conference the day the paper came out at Parliament House in Australia, with various people in our collaboration in Australia and other people who supported us on our journey. It was a very kind of exciting day, and obviously there were press conferences throughout the world in other places. And here is our Vice Chancellor, Brian Schmidt, explaining something about the gravitational waves to our chief scientist at the time, Alan Finkel. And I like to think it reminds me of this picture a little bit. And the point of this picture is to say that, unlike, light signals with optical telescopes and so on, we don't stop the signal. This signal that we did detect will go on, and maybe this alien race will detect it one day. So what did we learn from that initial detection? Well, it was the first direct detection of gravitational waves on Earth. It was the first detection of a black hole binary system. It was the first observation of black holes merging. And really importantly, from a general relativity theorist point of view, it was the first test of general relativity when the gravitational field is very strong and highly dynamical during the black hole merger. And, we've done all these tests of general relativity theory, not too long after Einstein presented the theory, but they all come from weak field gravity. And I guess it was still an open question as to really whether the theory would stand up in this very strong gravity regime. And it did. This earned the three founders of the LIGO projects the Nobel Prize in Physics for 2017, Ray Weiss, who kind of came up with the idea, the interferometer, received half. And probably another person, Ron Draver, would have shared in that, but he didn't quite live long enough. And then Barry Barish, who led the project from the 90s for quite some time and really got our act together and really made it happen. He received a quarter, as did Kip Thorne, who of course was a very important theorist, looking at the type of sources that we could detect with these detectors. Okay, I hope I have a few more minutes, Richard. I'd just like to say a few more things about what we've done since then, since this initial 100-year period, because really that was the end of one period and was the start of another, where we've opened this amazing tool to probe the universe in a way we've never had before. And Avi will continue on tomorrow to talk about how we can really precisely measure these properties of these events and so on. But on 17th of August 17, we made the first direct detection of a binary neutron star system merger. We thought this would be our first, but it wasn't. But we did eventually get one in our second observing run of advanced LIGO. So it's a binary neutron star in spiral, component masses in the neutron star expected range. We had 3 detectors on it on the day. And because of the directionality of it as well, we were able to really localize it well in terms of sky size, sky patch size to 28 square degrees. And it's still the closest and most precisely localized gravitational wave signal we've yet received. Amazingly, it was associated with the gamma ray burst detected by Fermi gamma ray burst monitor 1.7 seconds after we received our signal. And for years, these short gamma ray bursts had been detected, and really nobody knew what they were coming from precisely. And in that 1.7 seconds, we had this confirmation that at least a very good chunk of them are associated with neutron star mergers. And we sent out the signal to all the telescopes and satellites around the world, and they dropped everything, so to speak, and started searching for the counterpart for this gravitational wave signal. And this, in a sense, was the dawn of the age of gravitational wave astronomy. Here is an image on the left taken by the Hubble Space Telescope in April 2017, and then one obtained with the SWOPE telescope in South America on the day of the detection. And you can see that the kilonova of the neutron star merger has been located. So that happened within 11 hours of the gravitational wave detection. So for the first time ever, and actually the only time ever, we had a counterpart, which was totally amazing. So multi-messenger astronomy, you have a binary neutron star merger. We detect it with gravitational waves. We send out the alert to all our astronomy partners. And then if they can find it, first of all, they search for it. Then if they can find it, as they did for that binary neutron star merger, they will image it across the electromagnetic spectrum with light, radio waves, X-rays, and so on. And they will do this for days, weeks, and in that case, they're actually still doing it after years. And another amazing thing to come out of that was by imaging the kilonova, we saw that these neutron star mergers are the production factories of the heavy metals in the universe, like gold, platinum, and uranium. So this solved another very important mystery. This was what our detections looked like after the first 2 observing runs of advanced LIGO. The yellow dots down the bottom are the electromagnetic neutron stars, so the pulsars discovered in our galaxy. And the, God, I'm colorblind, but I'm going to say the pink, purple dots or something above the electromagnetically discovered or inferred black holes. And our discoveries are the blue ones at the top. And you can see already from these early discoveries, we're probing the black hole mass range. It's different to what we're getting from electromagnetic observations. And down the bottom, we have our first neutron star merger, which mysteriously produced an object in what we called the black hole mass gap between 2 and 5 solar masses. So, you know, what was it? Well, we think it's a black hole, but that was a question which came up very early after that detection. So the sort of questions that we probe now with these coalescences are, we refine the rate at which compact binary systems merge. We think about theories under which these binary systems form and evolve, e.g. in dense centers of galaxies or in isolated environments. We can want to probe the neutron star equation of state, which is, you know, a big mystery still, and that's will tell us so much information if we can actually probe that equation of state. We want to further probe the black hole mass gaps. There's actually 2, that lower one and a higher one due to pair instability. We want to know what's the least massive black hole and the most massive neutron star. Is there a preference for nearly equal component masses in our binary systems? And how fast do black holes spin? These are all the sort of questions we can probe with these continuing detections of compact binary systems. And this is what our detection stellar graveyard looked like after the first half of the 3rd observing run. We've done 3 runs so far, and this is after the first half. And as mentioned in the last talk, we now have over 90 of these detections. And you can see that we are continuing to probe this black hole mass gap between 2 and 5 solar masses. We have a number of objects sitting in that enigmatic range. And I'm just going to finish with a few exceptional detections we've made so far in chronological order. So 12th of April 19, we got a collision of 30 and 80 solar mass black holes. So at that stage, that was the most disparate sized in terms of ratio black holes that we detected so far. On Anzac Day, as we like to call it in Australia, and no doubt New Zealand, in 2019, we got our second binary neutron star merger. And unfortunately, we didn't have all detectors operating at that time. So we had a very large sky patch to send out, and unfortunately, the counterpart could not be found. So As I said, the first one was the only one where we've had a counterpart found. And it would have been good. I mean, this was a bit of an unusual binary system for galactic binary neutron stars as we know them from electromagnetic observations. It was kind of heavier and stuff, but we didn't get the counterpart. In 21st of May 2019, we had our most massive gravitational wave binary observed to date. And in the two component black holes were 66 and 85 solar masses. And that puts certainly the bigger one in this pair instability black hole mass gap. And that's why this diagram suggests, if you look at the left, that maybe these black holes were themselves formed from black hole mergers. But in any case, once these two black holes formed, they formed a 142 solar mass black hole. And this is the first clear detection ever of an intermediate mass black hole. So that was a very exciting detection. On the 14th of August 2019, we had the coalescence of a black hole and a mystery object of 2.6 solar masses. So we still don't really know exactly what it was, whether it was a really heavy neutron star, probably too heavy actually to be a neutron star, but we just don't know, or a very low mass black hole. So that was a mystery event. And then right near the end of our third observing run, which was our last one, because we had to take the detectors down in early 2020 because of the pandemic, and we needed to upgrade them anyway. On the 15th of January 20 and the 5th of January 20, we had our first confirmed binary black hole and neutron star collisions. So we expected one day to get these. So we completed the kind of trifecta and got this type of collision as well, although I point out we did not actually get a counterpart for various reasons. Okay, just very briefly, the future. I mean, don't get the idea that compact binary mergers are all we can do with ground-based detectors. They're not. And, you know, we're going to have a nice talk tomorrow, I'm sure, by Jade, who will be talking about supernova explosions. And, you know, we really wish in the future to understand the ignition of these supernovae through gravitational wave detections. So that's something we're definitely gunning for. Something which my group at ANU is currently working on, amongst other things, is to look at detecting continuous gravitational waves from spinning neutron stars with something like millimeter-sized mountains. So that creates the asymmetry, and they rotate and they form a continuous stream, which of course is much weaker than the other sort of waves that we're already detecting, and therefore it's going to take us longer to detect them. But by detecting them, perhaps in combination with electromagnetic observations, we hope to unlock the equation of state of neutron stars. And finally, we have the ability to call a gravitational wave detection of a gravitational wave that we don't know actually what it is. That hasn't happened yet, but it is very possible that we will have that happen in the future. Okay, and finally, this is the dawn of a new age, and perhaps the holy grail of gravitational wave science is that one day, with sufficient sensitivity, we want to actually observe back to pretty much the beginning of the universe and to understand the universe through our detection of gravitational waves. And on that note, I will finish, and thank you very much.
That was fantastic. I just realized I'd muted myself. If you were watching the chat, I had to briefly leave the room during your talk because it turns out part of our neighbour's fence had blown down. And the more alarming part is that our neighbour's fence is made out of large concrete bricks. localized gravitational wave events. I think we've got time for one or two questions before we break for lunch and then come back for the second session in the afternoon. But that was absolutely inspirational account of both past and also, I guess more importantly for many in the audience, where we're heading in the future. Just a question from earlier: an electromagnetic wave is self-perpetuating. I think I'm not sure exactly what's. I mean, an electromagnetic wave kind of chugs along in the electromagnetic field, but a gravitational wave must travel through space-time. So, Mia, do you want to clarify that a little, or are you, or should we take a stab at answering it?
Oh, sorry. I can explain it more if you want.
Sure. Yeah. No, that would be good.
Not explain it well. What I meant was electromagnetic wave, like when we learn about this in physics class, it is like the electric field changes and then magnetic field is created from this and then back and forth, so it keeps going by itself. But for gravitational wave, is it not like this? It must just travel through the space-time.
I don't know. That could go to any of us. That is a well-posed question, and it's a very elegant one because the dance between the electric and magnetic fields is part of what we teach. And certainly part of what I most enjoy. One of the things I most enjoy teaching is actually that precise topic. Does anyone want to have a crack at that? I don't want to greedily gobble it up all by myself.
I think we'll throw that to Jörg Frauendiener, who was talking about gravitational wave theory yesterday.
Jörg, are you online?
Thank you very much. Yeah, Mia, this is difficult. I would say that there is not so much difference between the electromagnetic waves and the gravitational waves, in the sense that this picture of electric and magnetic field, this is something that is observer dependent. And so you do see this only when you refer to an observer. Whereas the picture of the gravitational wave moving through space-time is a relativistic one already. So if one would introduce an observer like LIGO or so, then you would also see two different pieces of the gravitational wave that would go one into the other. It's just not done that way. And electromagnetism essentially is taught in a non-relativistic context. That's why you always have the electric and the magnetic field. But intrinsically, electromagnetism is just as invariant as the gravitational waves, and so I think it's just a question of an observer looking at things.
I think that maybe the even more natural question about that is that one of the interesting things about space-time is that we know that it not only is kind of stretchy, but also that it snaps back into shape once you remove the source of the stretchiness, if that makes sense. So, as the Earth, Susan showed that picture of the Earth and the Moon, but as the Earth rolls around the Sun, the dimple that it had made in space-time, heals as the, it's not like otherwise our gravitational field would be sort of like our shadow becoming detached from us. It would leave a sort of trench in space-time. And so if space-time was something more like wet sand, then we'd have this much more complicated gravitational dynamics. And so there is there's work being done on, memory and gravitational wave systems, but in general, we expect it to snap back. And anything that can kind of be bent and then snaps back, almost anything, that's basically the condition for for a substance that you can propagate a wave in, where you have, some cost of deformation and a restoring force. And so that property of space-time, in some sense, at completely the opposite end to the Jörg's explanation, which is like, if we do it properly in relativity, we treat the electromagnetic field as an antisymmetric tensor, so everything's good, right? But in this case, the kind of the high school example is anything that's stretchy and then restores to its original form once you take the stretching away. Most likely you can propagate a wave in that medium. That's really the minimal requirement. And so between those two things, maybe that but it's a beautiful question, because we do teach the electromagnetic wave as a kind of trade-off between these apparently two separate objects, but which are merged in a properly relativistic treatment of electromagnetism.
Okay. Thank you.
One more question, and then maybe it is lunchtime, because I imagine that people are getting a little peckish. And that is, how does the fitting of the initial black hole masses and the final mass work out from gravitational wave detections? And it's Susan's talk, but again, this is there's a whole bunch of people who just love this question.
Yeah, and we're going to hear about this tomorrow, so don't want to steal the thunder of Avi. I mean, obviously,
Exactly.
you know, we have template banks and things which we use, but yeah, Avi will be talking in more detail about how we work out the properties of our compact binary detections.
Can I ask a question briefly, Susan?
Yeah. Well, if people are happy to defer their lunch, that's fine.
Yeah, I mean, I guess what we can do is say, look, let's thank Susan for like an absolutely awesome talk. And those that want to you know, are feeling that they, you know, might be feeling the call of their stomach, you know, competing with the wonders of gravitational wave physics, then they can in good faith head off and get their lunch. And those of us who are in a position to chat for a bit can stay and chat for the next few minutes, and then we'll obviously be in a position to pick this up tomorrow as well. So thank you. Yeah, take it away.
Okay, so no, it's just a brief question. Can you say a little bit more about this mass gap, where this is coming from? Because somehow I missed that.
Yeah, so there's two like mass gaps, and one is the lower one, that from about 2 to 5 solar masses, and it's called a mass gap because basically the, you know, EM inferences of black hole masses don't fall in that range, and so, you know, it appeared to be a kind of gap. And you know, we are now finding objects through our binary detections which lie in that gap, either the, you know, the component, one of the component masses, or as we had with the binary neutron star detection, the first one where we got the counterpart, the resultant object fell clearly into that gap. And so we now have, you know, several objects in that mass gap. So we know it's not really a gap. There's stuff in there. And similarly, in the pair instability mass gap, the higher one, you know, that gap is proposed because the processes through which stars go supernovae and form, you know, neutron stars and black holes, you know, there's an issue in a certain part of the mass range where we don't expect to get black holes formed. And so now we're finding black holes in that upper mass gap. And, you know, the thinking is that they're probably formed from previous mergers of black holes, which may themselves be through, you know, supernovae processes or, you know, earlier mergers themselves. There's a whole kind of modeling thing going on about these binary systems as to how we can get, you know, well, the masses, but also the spins and the inclinations of the black holes, and, you know, how we can get the numbers of those that we're getting. What sort of situation are they formed in?
Okay, all right. So the mass gap is not really a mass gap.
No, not anymore. The more detections we get, the more we kind of destroy these mass gaps.
Okay, thank you.
Well,
Any other questions? Can gravitational waves reflect and form standing waves? Who wants to take that one?
well, we do have gravitational wave exact solutions, don't we, Jörg, in general relativity?
Yes, we do. We do.
And
Well,
do we have gravitational mirrors though, Jörg?
yes, you will see one this afternoon, I guess.
Gravitational cavity.
Gravi laser.
Yeah, Grazer.
Right.
That isn't science fiction. Anything else, folks, throwing around here?
And I'll be in probably tomorrow. So if you want to talk to me further, very happy. for those who were
Um,
around?
Okay. Otherwise, I think we'll bring it to a close here because it is kind of lunchtime. And so no, just thank you again for a fantastic and inspirational talk, and thank you also for making the effort to come to Auckland.
It's been a whale of a time so far. I must say.
On what turned out to be a somewhat more exciting day than we might have otherwise expected.
Yeah, lots
Next
of
time we'll
excitement.
make sure that you come on a nice day. But yeah, thank you very, very much, and looking forward to chatting in person tomorrow. Take care.
Okay.
You know, my Zoom background is actually Canberra. That took 2 months ago.
Okay. See you soon.
Okay. Ciao.
Yeah, see you in the afternoon.
I'm going to close the meeting room at this point.
Yeah.